Okay, today I'm going to talk about causal reliable broadcast, and we're going to continue writing code and doing specifications, making algorithms like we did last week. First, a very small refresher to get you up to speed. Remember last week we did reliable broadcast and uniform. Remember what uniform means? Remember what uniform means? You, that guy, right there, next to the pillar. No, you. Remember what it means? Not really. Well, it means that if a failed node delivers, all nodes deliver, so you're worried about failed nodes, whereas reliable is all or one only for correct nodes. We also went from P to eventually P. We did first this one with perfect failure detector, and it turns out miracles sometimes happen. It also works for eventually perfect, it's just a little bit less efficient. We did uniform for perfect, but that one we used a different technique. We didn't use an eventually perfect, we used a majority algorithm. This is a very common and important technique. In fact, there's two majorities, Remember, first we assume there's a majority of correct nodes, and then each node has to receive acknowledgments from a majority. Those are two different majorities, Because the one sending acknowledgments, they might fail after that. We don't know. Okay? And the trick is that the intersection of two majorities is non-empty. That means at least one correct node has got the message, and that correct node will do a best effort broadcast, and we're good. Okay? So majority is a very important technique. Okay? So you remember that, and you remember uniform, Okay. That was a refresher from last week. Now we make it even better. Okay, first a few seconds of silence for the people in Ukraine who are fighting for their freedom and for ours. Okay, so now we're going to talk about causal. We're going to add causality to the broadcast, and here's an example. Let's say we have a chat. People are discussing on the internet all over the world. And whenever they write an answer, it's reliably broadcast. That means all the nodes, all the people are getting all the messages, okay, if they're correct. But here's a possibility. These are three people. Ali says, "Are you sure?" Not E. Mrs. Y says, "Auditorium D at forum." Mr. X says, "Does anyone know where the lecture is today?" Actually, it's reversed. Mr. X asked a question, Mrs. Y replied, and Ali made another reply in that order. Okay? These people are completely imaginary, except for the Ali, who's a person I know. This is actually written for Sweden, for KTH, where they had these auditoriums. But you see, there's causality here. X causes Y. Y is a reply to X. And Ali's message is caused by Y. Okay, so there's two levels of causality. And reliable broadcast doesn't worry about that, because each broadcast is independent. For example, the Mr. X broadcast might be very slow. And the Ali broadcast might be very fast. So the reply for Ali might come before Mr. X. No guarantee, okay? So reliable broadcast does not guarantee between the different broadcasts. There's no connection between the broadcasts. Okay? Okay, question now. Well, we already did something more sophisticated, right? We did uniform reliable broadcast. This is very smart, sophisticated algorithm, so it must solve this problem, right? Does it? Does uniform reliable broadcast solve this problem? Yes or no? And explain. What does uniform mean? Okay, does uniform solve this problem? What do you think? Anybody have an answer? Be very careful. This is being recorded, and if you don't answer, everybody on YouTube will see how stupid you are. So please answer. Okay? They have to, this is the reputation of our university is at stake here. So, does uniform solve this? Take a guess. Yes?
UOB only makes guarantee that nodes will eventually receive the message, but not the order in which they receive the message?
Correct. Uniform only does guarantee about whether or not the message arrives. Uniform does not make any guarantee of the order between two broadcasts. It only says that if in one broadcast a failed node delivers, then all the correct nodes deliver. That's the same broadcast. If I have now another broadcast, the uniform does not make any connection between the two. Okay? So uniform does not solve this. Okay. We're going to solve it today. We're going to define causal reliable broadcast, where if you have multiple broadcasts that have some causal connection, the delivers are going to be guaranteed in causal order. So remember causal order that happened before relation that we saw a long time ago? And events can be happening before. They can also be the send and the receive. That's also causal, and then it's transitive. Okay? And here's the definition of causality for broadcast. Okay? These are two messages, M1 and M2. And they're both broadcasts, okay? Some kind of reliable broadcast. And there's a causal connection. We'll write it with an arrow. M1 causally precedes M2 if one of these three conditions holds. For example, C1 is called FIFO order, first in, first out. This is on the same node. If the same node broadcasts M1 before M2, then of course M1 is before M2. On a chat, if I make a message and a little bit later I make another message, well, the first one is before the second one. And the second condition is called network order. This is the send and the receive. I do a broadcast, it's sent to another node, it was delivered there, and then that node itself does a broadcast. So clearly there's a causal connection there. PI delivers M1 and broadcasts M2. And the final one that makes it tricky and hard is transitivity. You can have a long chain of causals. So if N1 is causally preceding M prime, and M prime causally precedes M2, then M1 causally precedes M2. This is recursive, you can see it, because this itself and this one is also causally preceding. So you can have a long chain of these guys. That's what makes it hard and interesting. Okay? Okay, so that's the definition. It's very similar to what we saw with Lamport's definition of causality. It's just that it's a little bit specialized on broadcast here. Here I'm looking at broadcasts, and not just any old events, just the broadcasts. Okay? Okay. So let's make an interface, specify this thing. Causal order. We define it, and we have two events. A request going down, and an indication coming up. So a CO broadcast, causal order, and a CO delivered. And this property holds. Let's define this property, CD, causal broadcast. If PI delivers M1, then it must have delivered every message causally preceding M1 before delivering M1. Okay, so if it delivers M1, then it has delivered all the causally preceding ones before. Okay, so this is the first cut. We add this, we make this property. So this algorithm satisfies this property. Okay. Let's say we only have this one property here. Only one, this one. So is this enough? Do we need more properties than this? Or not? What do you think? What's the easiest way for satisfying this one? This is not a hard question, no? What's the easiest way for satisfying CB?
Not sending messages.
Exactly. Basically, not delivering anything. It's an if-then. Your brains have to be wired to detect if-then properties. So there's a condition here. If PI delivers M1. And the way to make this thing vacuously true is that this condition is false. If PI does not deliver anything, then this property is not telling us anything. Okay? It's not adding anything. So what kind of property is this? Remember we saw these two kinds, huh? These two fundamentally different kinds of properties. What kind is this one? Remember the two kinds?
It should be a safety property.
Safety property, exactly. Because you can break it very easily, the system. You can deliver M1 without delivering a preceding message. That's it. It's broken. Okay? So you can break it in finite time. So it's a safety property. So this is not enough, huh? So you see, you have to be able to play around with properties, huh? If then, very important, huh? Safety liveness, very important. Okay? So I want you to kind of understand how the causality works. Here's two scenarios. And let's take a look at this first order. The first property of causality, the FIFO order. So here we have the scenario on the left, with two broadcasts and deliveries. Here also on the right, two broadcasts and deliveries. So which of these scenarios, or maybe both, is satisfying FIFO? So this is two broadcasts coming from the same node. So this is typically where we can apply FIFO property. So what about the left guy? Is he satisfying FIFO? What do you think? What do you think? No. Why not?
Because it first in, first out, so the first one is the second one.
Sorry, the second one?
No, the first one that entered doesn't go with this. I think.
Sorry, say that again. I'm not
I
getting
think
it.
I mixed, but I'm not sure.
So first in, first out means that if the sending is done in a certain order, delivery has to be done in the same order. Okay? So what's happening here?
That they are not in the same order.
Where is it not in the same order?
When I look into the arrows, probably it's not what I wanted. So where do we go?
Where is it not the same? P2. Because P2 delivers M2 before M1. So there's flipped here. Because M1 is very slow. So this one is not satisfying FIFO. Okay? What about the one on the right? It's not very hard, actually.
Correct.
This one is correct. 1 sent before 2, 1 delivered before 2, 1 delivered before 2. Okay? So that's FIFO. Okay? Here's another little exercise. This is network order. It means I send from one node to another node, and then that other node also does a send. Okay, so P1 sends, and it goes to P2, and then P2 sends. Some process PI delivers M1 and later broadcasts M2. So here, for example. So this one to the left, is it network order satisfied here? Is it?
Yes,
Yes. Why?
because both P2 and P3 first deliver M1,
And
and then
two.
P3 also delivers M2 in order.
Yes. Okay. So M1 is causally before M2, and both P1 and P3 are delivering M1 before M2. So what about the one on the right? The scenario on the right? Is this one satisfying network order? So again, M1 is causally preceding M2, and somebody else? M1 is causally preceding M2, so what happens on P1 and P3? What happens on P1? What's this? Delivery, M1 before M2. What's this?
M2 before M1, which is not allowed.
Which is not allowed, exactly. So in the scenario on the right, the network order is not satisfied. Huh? And now a more complicated one, transitivity. Okay. So here we have M1 broadcasting, and M2 broadcasts after, and then M3 broadcasts after. So there's a causal relation between these three guys. Okay, and each of the three, of course, is delivered on all three nodes. This one's a little bit harder. You have to look at three messages now. So what about the one on the left? Is it satisfying transitivity? No, why not?
Because message 1 is delivered after M2 and M3 on P1.
Right. Message 1 is causally before M2, but it's delivered after. So this one is not transitive. What about the one on the right here? There's arrows going everywhere, so you have to look at every node here. Look at all three arrows on every node. So here, for example, what's happening here? And here, P2, and on P3. So what's going on here?
Sounds good.
It's good, right? M1, M2, M3, M1, M2, M3, 1, 2, 3, and 1, 2, 3 are in causal order. So it's only the left one that's not satisfying. Okay? See, so before writing code, it's very important to understand the properties. Okay? That's always true, but in distributed systems especially, because a small change can make a big difference. And here's an example. Let's say I have two definitions of causality. So here again, I want to change around. I want to do specification engineering. Before writing any code, think carefully. CB is the property we had before. If PI delivers M1, then PI must deliver every message causally preceding M1 before M1. Okay? But I make a variation of this, CB prime. If PJ delivers M1 and M2, and M1 is causally preceding M2, then PJ must deliver M1 before M2. Okay, so PJ delivers both, and there's a causal connection, so it must deliver in this order. So that's slightly different. But now I want to compare these two. How are they different exactly? Okay, what's the difference? Okay, so I've given already some hints. What is the first thing you should look at when you see properties like that? What is the thing you should look at? Tell me now. To analyze properties like that. The first thing, immediately, you should look at.
Predicate of the if.
The predicate of the if, exactly. They're both if-then properties. And what are the ifs here? Here in the first one, it's if Pi delivers M1. What is the if in the second case? If Pj delivers M1 and M2. Okay? So here I'm only assuming one delivery. Here I'm assuming already two deliveries. Okay? So if only one message is delivered, which of those two properties applies then? If only one message is delivered, only first one, huh? This makes a stronger assumption. So CB prime is actually weaker than the other one. So let's look at some scenario here. Okay. So here's a scenario on the left. Okay. M1 before M2 before M3. But M2 here is delivered before M1. So P1 is delivering M1. Okay. P1 is delivering M2. If P1 delivers a message, M2, it must have delivered every causally preceding message before. But M1 is causally preceding, but it's not delivered before. So CB is violated here, right? But CB prime is also violated because P1 is delivering both M1 and M2, and M1 is before M2, but it's not delivering M1 before M2. And so the scenario on the left is violating both of these conditions. But the scenario on the right is only violating CB, not CB prime. So what's going on here on the right? Okay, so again we have M1 before M2 before M3. Here on P1 we have 1, 2, 3. On P2 we have 1, 2, 3, fine. On P3 we only have 2, M2 and M3. So M1, it disappears. It's not, the message, poof, disappears. It's not delivered, okay? So, do we accept this? Well, CB does not accept this because here I'm delivering M2, but M1 is before M2 and I'm not delivering it. So that violates CB. But it does not violate CB prime. Why not? Why does this not violate CB prime? This one on the right. It's here, let's go what's going on. It's at P3, yeah? This is not violating CB prime. Why not? Why not? You tell me.
Because P3 doesn't deliver M1 at all.
Because it doesn't deliver M1 at all. Exactly. CB prime assumes that it delivers both, and then it determines the order. So if the message is not delivered, CB prime doesn't care. Okay? So CB prime doesn't care about lost messages. So that's kind of not good. CB prime is actually not that good then, actually, huh? This doesn't really care about lost messages, whereas CB does care. Whenever you deliver one message, all the causally preceding ones have to be delivered too. So CB really cares, huh? So you can actually say that CB implies CB prime. If CB is true, then CB prime is true, but not inversely, yeah? CB is actually more demanding, in a sense, than CB prime, huh? Okay? So little differences in specification are important. Okay, you see that? And remember also, if you have if then, always look at the if condition, huh? You have to always look at the if condition. And properties that might seem almost the same, maybe they're not really the same, okay? Because the condition in this one, CB prime, it only works when both of these two messages are delivered. But if you don't deliver, CB prime doesn't care, okay? So this kind of thinking is very important. And we're not even writing code yet, huh? Okay? It's very important. Okay. Okay, now let's look at the full interface. So this is reliable causal order. We have a broadcast and a delivery, so a request and an indication. And what we do is we actually are going to build on what we know. We're going to take the four RB1 to RB4, the four properties of the regular reliable broadcast. And we just add CB to that. How come that is very modular, huh? We divide the specification into pieces, we keep the old one, we just add something to it. That's very nice, right? We don't have to tweak these guys at all, we just keep them. How come it works? Because RB1, RB4 only is telling us about single messages that are broadcast. A single broadcast satisfies this. Whereas CB is telling us how messages are connected, multiple messages, because of causality. So they're kind of orthogonal to each other, huh? So it's very nice to have a specification like that, huh? And it doesn't matter. CB is a safety, so we're adding a safety property. That means that we're actually pruning executions. You see, if we don't have CB, then we can have all kinds of weird executions where the orders are weird and different and bad. But if we add CB, we're kind of forbidding all the bad executions. We're pruning the set of executions. Okay, we're removing the bad ones, and we're keeping only the good ones. So that's very nice. So if we have only RB1 to RB4, we have a certain set of executions, and we add CB, conjunction to that, and we have the subset. We're pruning, okay? So that's very nice. That's a very good way to make specifications. Start with something really general, and then add something to prune it, okay? Okay, so that's how we're going to do that. And for the uniform, it's almost exactly the same. We're going to have uniform, reliable, causal order. Complicated thing here, URCO here. A broadcast going down and a delivered going up. And again, we keep the four properties from uniform, reliable broadcast, but these are almost the same as reliable. Huh? The only difference is what's called the agreement, the all or none property. Huh? So regular reliable broadcast, if any correct node delivers, they all do, all or none. And uniform reliable is if any node, including failed nodes, deliver, then they all do. So the uniform, the only difference is it also worries about the failed nodes, and we just add CB to this again. You see, so the specification is very nice and simple. Huh? You start with something very general, and then you just add safety properties to reduce the set of allowed executions. That's a very nice way to make specifications. Huh? So now we have, we're starting to have a nice specification. Now we can start implementing. You see, I spent quite a bit of time thinking about the specification before writing code. This is very hard in general because people love to write code and they think that specifying is kind of a waste of time because the code is what's doing something, right? So engineers, they love to write code. So you have to resist the impulse to start writing code very fast. So now we've done some thinking about the spec, and now we can build it. So we're going to use the code for reliable to make the causal. So we're going to build our layered system. Remember we had last week this reliable broadcast, which was built on top of best effort. And sometimes we even had a failure detector there. So what we're going to do this week is we're going to add, maybe I change color. We're going to build on top of that. So our causal broadcast is going to look like this. So all this code is the same. So we're only going to write this little piece of extra code. Okay? That's a really nice way to build systems if you design the specs right. So here you have a reliable broadcast. Here you have a reliable deliver. Here I have causal order broadcast, causal order deliver. So if I do causal order broadcast, this algorithm will use reliable broadcast to do stuff, and eventually it will do causal order deliver. Okay? So that's how we're going to do. We're going to use last week's code, which I'm not going to write again. We're just going to use it. Okay? I'm only going to show you this code for the causal part. So we build this thing in layers. So a very complicated algorithm, if you do it right, in layers, the layers are all simple. Okay? I remember the example last week where we wanted to write an algorithm where you could broadcast the same message more than once. Whereas here, the messages are assumed to be unique. Well, you just build a layer on top. Okay? Layer on top. That's the computer science way. You build, once you have an abstraction, you build a new abstraction on top. Okay? That's a very good way. Okay, so how do we implement this thing now? Actually, it's very easy if you think about it. We're going to use this reliable broadcast, but when we do a causal order broadcast, we're going to do reliable broadcast, but not of the same message, of some other thing. Okay? So we're going to use the reliable broadcast as primitive, but we're not going to have exactly the same message. We're going to use it as a tool. And the idea is that we're going to piggyback something. And we're going to piggyback the history. History, what I call history, is the set of all causally preceding messages. Okay? Whenever I do a causal order, whenever I do a broadcast here I'm going to send a message, which is this message, plus a list of all the causally preceding messages, which I'm keeping track of. Okay? And that means when I deliver, I will immediately know what are the causally preceding messages. So if there's any I didn't deliver yet, I can deliver them. Okay? That's nice, huh? That's pretty nice, right? It's very simple. It's very simple. Each message, M, will carry an ordered list of all causally preceding messages. So there's a variable that I'll call passM, which is a list, an ordered sequence of all causally preceding messages in order. Okay? And whenever a node RB delivers here, RB delivers, it will look at past, and it will CO deliver all the causally preceding messages. So this RB is both M plus past M. That's coming up here. And here I will take a look at this list, and if there's any messages in here that I have not delivered yet, then I will deliver them before delivering M. Okay? So I guarantee that all the causally preceding messages get delivered before M. Okay? And I use the same trick to avoid duplicates. I have a delivered set. So whenever I deliver, I add it to that set, okay? Because of course, when I send many messages, the pasts are going to be like resembling each other. So it might be that I'm sending very often almost the same list. So, okay, so let me show you kind of an example of how this executes. Okay, so here's example. I'm doing causal order broadcast of M1. So the M1 is delivered here. The M1 is delivered there. Okay, very good. Okay. So here I'm doing a causal order deliver of M1, causal order deliver of M2. So I'm going to use the little red boxes to show that it's actually delivered. If it's not a red box, it hasn't been delivered yet. Okay. Now I do a second one, causal order of M2. And so what I send here is M2, and this is the list of preceding messages. So M1, it's only one here. This is just a list of one element. So I'm sending M2 with a list of all the messages, and I'm sending it also here. Okay. So far nothing is delivered yet. Okay. Okay, I deliver it. I notice that M1 has already been delivered, so I can deliver M2 right away. Here also I deliver M2. Okay. Okay. And here, assume this one goes very fast. This one arrives here, but this one is still in the network. This old M1. But M1 is before M2. So M2 arrives here with the M1 piggyback, and this RB delivers. So that's the green one. It RB delivers, but it has not CO delivered yet. So I make a difference between RB deliver and CO deliver. So I RB deliver M2. But now I have to be very careful, because I have to deliver all the preceding messages, all the ones that are preceding M2, I have to deliver them before M2. That means M1 has not been delivered yet, so it means I have to deliver M1 first, and then M2. So I look at the list here, and I see that I have to deliver this one first. And when all these past guys are delivered, then I deliver M2, and the two red ones. So this single green RB deliver will give you two red CO delivers. You see that? A single message coming up here, it will cause two messages to go out. CO. And then finally M1 arrives. And what happens when M1 RB delivers? What happens? What happens when this one finally arrives and doesn't RB deliver? What happens here? You tell me. Tell me. What happens? What happens here? It's not a hard question, huh? What happens here? I heard something. Oh, come on. I've already delivered M1 and M2. So what happens here? Say it. What happens here? Nothing, huh? M1 arrives here, but M1 has already been delivered. It's in the delivered set. So nothing is delivered. Fine.
How could it deliver M1 if you didn't receive it yet?
But it has already been received here. Because of the past list.
So the message contains the history of all the entire...
Yes! You're getting it. Yes, indeed.
Doesn't that create an enormous package?
Absolutely. Of course it does. But it has one main advantage. It's correct. Okay, you see, this is very good because people have this tendency to optimize. Well, don't worry. We will optimize, so you will be happy. But I first want a correct algorithm Sure, this past is going to grow, and I will talk about it. Huh? So we're going to take care of that past list. But first step is always a correct algorithm. Huh? So this is easy to see it's correct. Huh? It's very easy to see. And once you see it's correct, then you optimize. Okay? See? Okay. That's a very good comment. Okay? So I'm very happy. Here's another slightly different scenario. This one I call indirect override. Because here it's P2 that's doing the second broadcast. So P1 broadcasts here, and the red ones, the two are delivered here. But notice this one again is kind of slow, it's still traveling, the M1. But P2 has already CO delivered M1, and it does another broadcast, P2. And it also piggybacks M1. So this M1, which was coming from P1, is now sent from P2, okay? So here and here, okay? And I call it indirect override because this guy is in some sense overriding this guy because he's earlier. Okay, so there's the two CL delivers. And what happens here? Well, this is kind of the same as before. I do an RB deliver of M2, a green one. So the user does not see this, huh? This is hidden inside, huh? It's inside the algorithm, huh? And then I have to make sure that all the causally preceding messages, preceding M2 are delivered. So I deliver M1 and M2. And then M1 arrives, it does an RB deliver, which does nothing, okay, and it's done. Okay, you see that? So it's a very nice algorithm, huh? There's a minor efficiency problem, but it's correct. But first, let me show you the code of this algorithm. This algorithm, reliable causal order broadcast, it uses reliable broadcast. So I'm building it like this, layer on top of RB. I have my delivered set and the past set, which is all the causally preceding messages delivered on that node. Okay. I do RCO broadcast. So this is the request go down. And this causes an RB broadcast to go down. But it also adds M to the past list. The past list is always growing. Anytime I have a causal message causally connected to the broadcast, I'm going to add it to the past. Okay, I have one more page of code, and that's it. This is the whole code. If I get an RB deliver, then I have to do stuff. Okay, the RB deliver coming up here. First of all, okay, I only do something if M has not been delivered yet. So there's this big if here. And then I do a for loop for all messages in the past list, of course in ascending order. That means I start with the oldest ones. The order is important. If N is not delivered yet, then I RCO deliver it. And I add it to the delivered set, and I add it to the past. Every RCO deliver is added to the past. Okay. Notice this past M here is the message, is the past coming in. These are all the messages that are behind M, past M from the sender. And so these are the ones I look at. And if I actually deliver it here, then I add it to my local past. Okay, so past and past M, don't confuse them. And once I do this, I can do the RCO deliver of M. I add it to the delivered set, and I can add M itself to the past list. So it's very logical, right? It's very straightforward and logical, isn't it? Okay. So I deliver the preceding messages. I append when I do that. I deliver the current message, M. I also have to append it. So I'm always managing my history. Whenever I deliver, I have to add something to the past. And of course, passM can be very big. Okay, that's something we talked about. But let's first prove the correctness of this. We can actually prove the correctness, and again, it's based on RB. Remember, we have RB1, RB4, and CB, the two pieces of the specification. And we can prove them separately. So the first thing we have to show is that RB1, RB4 is still holding, okay? Because it holds for RB. So it's clear RB is not creating and not duplicating. Huh? That was two of those properties. And we're only adding past to the RBs. We're not adding anything more. Okay, so we still satisfy that. And validity, this is the actual broadcast. Huh? If it's broadcast, it's delivered. The only difference is some messages might be delivered earlier. Because they're in the past list. But they're still delivered, so that's holding, okay? And the agreement, which means if any correct node delivers, they all deliver. So this, again, it's not changed because we're still doing RB broadcast of the same messages, okay? The past list is only changing the order. It's not changing which messages. That means you can prove that RB1, RB4 are still holding the way that CB uses it. So that's very nice because it's actually a quite complicated algorithm, huh? Causal order, fault tolerant, concurrent, distributed, okay? The second piece is the CB property, causality. This is a little bit harder, so I'm not going to go off through it in detail. The way to do it is to follow the executions, okay, the deliveries, okay, and whenever you add one event, so you assume it's true for some, up to some point, whenever you add one event, you can see that the causality is respected. That means if we have an RB deliver, we are adding all the past previous events. So we're maintaining CB, okay? So basically you can prove it like that. Up to a point, and you add an event, and it's still true. Because of how we define past, okay? Okay, so that's good. We have actually a correct algorithm here, huh? Okay, there was a very nice comment, which is completely correct. The message size is growing a lot. So, the message size is growing terribly much. So we can fix that, of course. But the first thing is correctness. Huh? Notice that we actually have quite a sophisticated algorithm here. Huh? Remember, we tweaked the specification to be very strong. Whenever I deliver a message, all causally preceding ones are delivered before. Very strong. It's also fault tolerant, concurrent, distributed, and anybody can broadcast at any time. Any node can do a broadcast at any time, and it works. That's not bad, okay? So it's correct. That's a good property. So the disadvantage is the message size is growing. So now we have a correct algorithm. Let's fix that. Okay. So one way to fix that is to do garbage collection. Okay, so I'm going to show you how to do that. Garbage collection means whenever there's messages that you don't need anymore, remove them. Okay? And that's the first thing we're going to do. There is a small problem with garbage collection. It requires a perfect failure detector. That's a pain. Okay, we're going to assume a perfect failure detector. That's a general problem with garbage collection in distributed systems. It's actually quite hard, and if you want to do it really, really well, you'll need a perfect failure detector. So the idea is, when all correct nodes got the message M, then you don't need it anymore, and you can remove it from the past list. So eventually, all the correct nodes will be getting M. Okay, so with this algorithm, every time we know that the correct nodes all got M, there's no need to keep it in the passed list anymore. So you delete it. So that means the passed list will always be shrinking. Huh? Okay? Okay, I'm going to show you the code for that. But I'll show you the code after the break. So we do break, and then I'll show you how to do garbage collection. Fairly close. The problem with the algorithm I showed before is, as was very pertinently remarked but before the break, is that the message size is going to keep growing forever. So that's not very nice. So now that we have a correct algorithm, let's try to optimize it. And we're going to implement a garbage collector. That'll be our first way to optimize it. In order to do that, we need a perfect failure detector. Because we're going to keep track when all the correct nodes have gotten M, then there's no need to keep M in passed anymore. And then we can remove it. And so while the algorithm is running, the passed list is going to keep shrinking all the time. And so that's garbage collection. Okay? So here's the code. This code is modular. So we just add it to the code we've already done. We have a few extra things. We have our crash here from our perfect failure detector. We add a few local variables. So the array of acknowledgements. Okay. Which nodes have acknowledged message M? So each message, this array is indexed by the message. Okay. And for each message, it keeps a set of nodes that have acknowledged. Correct is the set of correct nodes. Starts out by being all nodes from 1 to N. Okay. So when I get a crash message, I will remove it. Correct? And then we have two extra methods here. This one, whenever we do a CO deliver, okay, then notice this message here. I've added it, I've designed it so that whenever we do a CO deliver, this guy will also be executed. M is delivered. As soon as M is delivered, and the acknowledgement is not, the node has not acknowledged itself yet, so it starts out by being empty. Then I add itself to it. So this is kind of like to make sure that I only execute this guy once, and I do an RB broadcast. Okay? I do an RB broadcast so that everybody, all the correct nodes, will get the acknowledgement. Okay? So the acknowledgement is sent to everybody, and when a node receives the acknowledgement, it adds the node that it's acknowledging from. PI is added to act M. This is on all the other nodes. And if all correct nodes have acknowledged, so I read this if, so correct is a subset of act M. That means if all correct nodes have acknowledged, then I can remove this message from the past. So I assume that there's this operation remove. Okay? And that's it. Okay? So that's not so difficult, actually. It's one page of code. And just a small thing I want to mention on this. This is actually modular in interesting ways. So I have to explain this to you. So for the CB, I have the algorithm, but I also have the GC. This code, I don't have to really change. I mean, the init, I've added two things here, but these three message blocks, I just add them, okay, to the previous code. So this code is modular. So everything is modular, So this piece, so I reuse this, I use this, I use this, I just add codes. So I have a modular implementation. But I also have a modular specification. Just want to remind you of that. RB1 to RB4 plus CB, which I just add. And here is just pieces of code I'm adding. Everything is designed so carefully that I just have to add, and the previous code is still correct. Okay? so that's the garbage collector. That will cause the pass to shrink and keep it small. Okay? Still some questions though. So first the question for you guys, see whether you understand. What about the ACs? The ACM array in the previous code is also growing, of course. So it seems like I'm not solving anything. This ACM array also keeps growing. So what do? I have to garbage collect the ACK array. How do I do that? Aha. It's actually not hard. When do I need the ACM value? At some point, I don't need ACM anymore. And at that point, I can remove it. So I can garbage collect.
Maybe when we remove from past, we can also get rid of the act.
Exactly. When you remove from past, at this point, so I'm removing M from the past. So I don't need act M anymore. It served its purpose. So I can also remove that piece of act M. Huh? Okay? So actually there's no problem there. Okay? I can garbage collect the acts easily. And then the very important question, I have defined the garbage collector using a perfect failure detector. What happens if we use an eventually perfect? Does it still work? That would be wonderful, right? Please, let there be a miracle. Does it still work? What do you think? If I replace P by eventually P in there, will it still work? What do you think? Will it still work? Huh? I put an eventually perfect one there. So you remember what the eventually perfect, what it does compared to perfect, huh? It can make mistakes for a short time, for a certain time, but then eventually it doesn't make mistakes anymore. Is that okay here? What happens if there's a mistake? Yeah?
If there's a mistake, we lose the chain of causality, and then the properties of
yes.
are broken.
If there is a mistake, we incorrectly assume PI has crashed and it's still alive. That means we will remove a message from past even if that node has not received it yet. So we break the chain of causality, so it doesn't work. Unfortunately, that would have been way too nice. But in fact, that's a general issue. Garbage collection is very hard in a distributed system. This garbage collector will only really work if you have a perfect failure detector. So what do we do? Now assume we want to run this thing on the internet now, okay? We always are going for that. Well, I will show you another implementation that is going to work in that case, where you don't have these growing sets of past messages, okay? And it's a very interesting technique that you can use very generally. It's actually a very general idea. In fact, it's a whole area of mathematics called abstract interpretation, but I'm not going to go into that. I'll just show you this, but this technique, you have to remember, it's very powerful and you can use it very often. Okay, so let's explain. So the first algorithm we did, each message has a history, all the past messages, all the causally preceding messages, okay? Now, can we get by with less, with something smaller than that? Okay, can we get by with something smaller? What is smaller? I mean, maybe we don't really have to know all the actual messages, because they will be arriving anyway, okay? They might be arriving later, but all the messages will eventually be arriving. So maybe we don't really have to know all the messages. But what do we need to know then? We need to know something. We need to know some causal information.
Just the order, maybe.
The order. How do we know the order?
Oh.
Yeah, that's a good point. That's a good suggestion.
We can,
Yeah.
I don't know, have
Something like that. Yeah, you're on the right track. That's exactly the way you have to think. And we don't really have to know the messages, we have to know the order. But we actually saw a way to keep track of causality. Huh? We saw these logical clocks. And in fact, if we, remember we saw Lamport clock and vector clock? Well, actually, we can use a vector clock instead of the whole list. A vector clock is just an array of a fixed size. So the size is not growing. But you have to understand what it's doing here. The vector clock is not keeping track of the messages, but only the number of messages. The vector clock will tell you how many causally preceding messages on each node that are known, okay, that I know on each node. So I just know the number of messages. And if I do that, then basically I just have to wait until a certain number of messages have arrived from that node, and then I'm ready. So basically, the trick is not to keep track of the actual messages, but just the number of messages that I have to wait for from each node. The ones that are causally before. And the vector timestamp can tell me that. So that's kind of the idea. But first, so let's go into a little bit detail how that would work. Okay? So instead of representing a list of messages, which is very long and growing, we will represent it by a vector clock, which is just an array. Now for each node it gives you a number. So the sum of all the numbers in this array will actually be the length of the past history. Now the vector clock tells you how many past messages are on each node, in fact. So we have to compute this vector clock. And we saw how to compute vector clock. So it's an array. At each node, it's an array of n. So at node pi, the VC, the vector clock of I itself, is the number of messages that are causally preceding the current one on that node itself. Okay, the number of messages I see I'll broadcast, and the element of the vector clock for another index is the number of messages that node I has gotten from node J. So it knows that there are at least that many causally preceding. Okay, so I'm counting basically all the causally preceding messages that were broadcast from all the nodes. Okay? Note, there's actually, this definition is actually a little bit different from what we saw before. In the previous definition of vector clock, we counted all events. Okay? How many all events? Here we're only counting broadcast events. We don't care about other kinds of events. We're only counting the number of broadcasts, okay, and CL deliveries. So it's like a customized version of the vector clock that's only counting the events that are important for us, which are the broadcast events. If the algorithm is doing other stuff, there's other event things going on, we don't care. We only care about the broadcast events. So the vector clock will tell me how many causally preceding messages there are at a particular node, but kind of ranked from each. How many from node 1, how many from node 2, and so the total number of causally preceding messages will be the sum of all of them. So instead of keeping the whole past, we just have to keep that, basically. Okay? So how does it work? Well, I'm going to show you a scenario because it's kind of, you have to see how it works to really get it. Again, we're going to piggyback. Whenever I do a CU broadcast, I'm going to do an RB broadcast, just like before. But instead of piggybacking the whole pass list, I'm only going to piggyback the current vector clock. So it's just an array, a fixed size, and each node only has to keep track of that array, a fixed size, okay? And when a node receives an RB delivery with a vector clock, it will compare the received vector clock, VCM, with the local vector clock. Okay, you see that? The received vector clock and the local one. The local one tells me how many messages that are in the past on that node. The received one tells me how many messages in the past for M. And if there's a gap between the two, if M somehow needs more messages, then I have to wait. Okay? So there's a condition. So I compare the vector clock attached to M with the local vector clock. And when messages are arriving, so this will be like a thing that's happening. I put that on my node, I, and each time a message arrives, the local vector clock will be increasing. And if there's a gap, if VCM is higher than VCI, that means the M has more causally preceding messages. That means I have to wait until they arrive. So the VCI will be increasing. You see kind of how it works? But I'll show you an example. So you have to wait until the local vector clock has caught up to VCM. And then you can deliver. And it will catch up because those messages will be coming in, okay? So here I have to show you an example now to show you how it works. Okay, so here I have three nodes. The three vector clocks are 0, 0, 0. Okay? I do a broadcast. After the broadcast, it becomes 1, 0, 0. So the piggyback is the number of causally preceding broadcasts. So it's 0, 0, 0. There's no preceding broadcasts. 0, 0, 0. Okay? See that? Okay, let's go on. This one is delivered. That one is delivered. Once it's delivered, the local vector clock gets incremented. And this one, it's okay. I can deliver it. But I will show you a case where you have to wait. They're the same. Let's now do another broadcast here. So after this broadcast, the vector clock will be 2, 0, 0 because there's two broadcasts. But the piggyback is 1 because there's one message before M2, this one. So the piggyback vector will be 1, 0, 0. 1, 0, 0, 1, 0, 0. Okay, now what happens? Okay. Okay, it's delivered there. It's delivered there. But here, what happens? Well, this number, 1, 0, 0, is bigger than 0, 0, 0. The 1 here means there's actually one message from P1 that is causally before M2. But here it's a 0. That means that message has not arrived here yet. You see that? See what's happening? The 1 is telling me that the M2 is actually a little bit ahead. There has to be another message coming from M1 before M2. It's actually this one, Okay, but I don't know about M1 here, I received the 1, 0, 0, and I compare these two vector clocks, but this one is still lower than that one, so I cannot deliver M2 yet. There's a gap. You see what's going on there? There's one message here that has to come that has not come yet because it's a 0. Okay, so you see how it's working, And now that M1 finally arrives. So this one is not doing anything yet. It's on hold. The M1 is very slow. Finally arrives. 0, 0, 0. So M1 does not require any preceding causal message. So this is the same as this one, so we're fine. There's no gap, so we can deliver M1. And then we have the local vector clock become 1, 1, 1. And now the gap is closed. You see that? This message has arrived. I have 1, 1, 1, 0, 0, and this is 1, 0, 0, so I'm good. So now I can actually deliver M2 as well. So I've held it locally until the comparison between the two vector clocks is satisfied. Huh? So now I can actually deliver M2. You see the idea how it's working? Right? Okay. Of course, the devil is in the details. So I have to show you some code here. Okay, so there's 2 pages of code. It's not very, very complicated. You have to just reason a little bit. So I'm doing the R. So again, the initialization, I set the vector clock to all zeros. And now I do an RCL broadcast, and I do an RB broadcast. So this is going down here. And I will piggyback my local vector clock to the M. I'm sending M plus the local vector clock. And then I will increment the index of my process, self, and I will do RCO deliver. So I can do the local RCO deliver right away. Okay, so this is now the code. Now we have an RB deliver. But we have an RB deliver, this, coming up. But we can't do RCO deliver just yet. You have to be very careful. So what do? So we get M with VCM. We put it in a special set called pending, okay, where it keeps track of the node Pj and this vector, okay? So we keep track of that. But that's all we do. And then we have this procedure called deliver pending, and this is the one that decides whether we can RCO deliver or not. So this is kind of like a for loop here. If there exists an element of pending such that VC is less than or equal to VCM less than or equal to VC, then I can RCO deliver. So basically, whenever messages arrive, okay, sorry, whenever I RCO deliver, I will update my local vector clock, okay, here. And that might make more messages able to be delivered. So the VC will be growing as long as I'm delivering here. Okay? So this is like a for loop. While there exists, so I'm looping through this pending set. And as long as I can find an element such that this holds, then I RCO deliver it, I increase I update the vector clock, and I keep going. So this loop will actually keep going until there's no more messages that are satisfying the condition. Because in a real system, you might have hundreds of messages coming in. So the fact that one message arrives, it might allow another message to be delivered. So here, if I look at the previous code here, the fact that this message arrives will allow this message to be delivered. But there might be more of them. Here I only have one, but I might have a whole pile of them here. And they're all waiting to be delivered, but there's a gap. But when this one arrives, then M2 can be delivered. But when M2 is delivered, then M3 can be delivered. There might be a whole bunch of them, M4, M5, M6. Okay? So it's like a kind of fixed point computation. It keeps going until there's no more possibilities. Because it might be a long chain of them. See how it works? Okay. For every message whose VCM precedes the local VC, that means that there's no gap. The local VC has caught up. Okay. I removed it, I deliver it, and I increase the local VC. So that's it, okay? It's basically taking advantage of what the vector clock is telling me. The vector clock is a summary of how many causally preceding messages there are. So this is doing exactly the same as the previous algorithm, but just with the summary, not with the whole list. Okay, let me show you an example. So here's an example. I have two nodes here, okay? P1 and P2, and the vector clocks are 0, 0. This one does a broadcast. So the local vector clock becomes 1, 0. But the M1 is then sent, but the piggyback is 0, 0. Okay? Okay, it delivers there. Now let's, just to make it interesting, let's say P2 does a broadcast here. The local vector clock becomes 0, 1. This one is sending a message M2 to P1 with the past is 0, 0. The M2 doesn't require any messages. And now what happens? So this one actually delivers. But notice what happened is this one and this one actually has even higher than this one. It's not like, usually you want this one to catch up, but it actually got farther even than M2. It's 1, 0 compared to 0, 0. But that's fine. It's fine because it's like concurrent events, okay? There can be other events coming in that are not causally related to M2, and that's okay. So M2 arrives here, and then you have, since this one is coming from P2, you get 1, 1 here. This second one is because it's coming from the second node. Okay. And the same thing happens here. This M1 arrives here, but notice the local 0, 1 is actually higher than 0, 0, but that's okay. There's an extra guy here, because this one, but this one is not causally connected to M1. So it's not, it's there, but it's not hurting anything, but it's also not helping. It's just there, so it's allowed to be higher. Okay? And then once this one is delivered, you get 1, 1 instead of 0, 1, because this first one is because it's coming from P1. Okay? Okay, fine. So this is a possible execution, right? There's just one curiosity here. P1 delivers M1 before M2, and P2 delivers M2 before M1, but I was talking about causal delivery. How come the delivery order is not the same? Shouldn't it be the same? I have to worry about causal delivery, right? The causality is the same everywhere, right? So what's wrong? Is there anything wrong? What's going on here? Yeah?
The messages aren't related.
The messages aren't related, yes, very good. They are concurrent, actually. These two broadcasts have no causal connection to each other, and in that case, the algorithm will do no effort to make them maintain any order whatsoever. So the fact that they are delivered in different order doesn't matter, because they have no causal connection. So this algorithm will actually only enforce the order for messages that are causally related among each other. So this is actually a consequence of how the vector clocks work, if you look at it. Okay? So nothing is wrong. There's no causality here. Okay, so let me now do some exercises. some exercises. We have seen causal order. We actually also saw total order, and I'm going to define something called FIFO order, or single source FIFO order, because causal order is not the only order between messages. Single source FIFO order is actually a weaker thing than causality. It's like there's no transitivity anymore. It's only between two nodes. The messages going from one node to the other are delivered in the same order. They never switch orders. Okay? For messages M1 and M2 and PI, PJ, if PI broadcasts M1 before M2 and PJ delivers both of them, then it will deliver M1 before M2. So the order doesn't change. Okay? Notice, what you notice immediately on this condition, it's actually written there, but always look at the if condition. This should be a reflex, okay? So what are the if conditions here? Well, PI broadcasts M1 before M2, but there's an if condition here. What does it say? If Pij delivers M1 and M2. So this is only telling me something in the case that both messages arrive, okay? Doesn't require delivery of both messages, okay? It's actually only enforcing the order for the actually delivered messages. Okay, so this is kind of a weaker thing than causality, huh? This is only worrying about two nodes, whereas causality is all nodes are connected from causality because of transitivity, huh? Whereas this one is only worrying about pairs of nodes, so it's like a weak form of causality, the FIFO. Here's another order, total order. This is also something we saw, but I want to give you a precise definition. So the idea is everybody is delivering in exactly the same order. So what is the formal property? For all messages and all PI, PJ, if both PI and PJ are delivering both messages, then they deliver them in the same order. So again, little alarm bells have to be ringing. This formulation does not require delivery of both messages. Another thing is, everyone delivers in the same order. That order is not necessarily the order in which they were sent. They're delivered in the same order, but they may not have been sent in that order, as long as they're delivered in the same order. Okay? So that's total order. So now that you've seen these two definitions, notice neither of them require delivery. Now we're going to show you do some exercises. It's very good to do exercises. So here's a scenario. A is a broadcasting here. So B is broadcasting. These are deliveries. A, B here, B, A. And now I have three questions for you. Yes?
I have one question for you.
Okay, thank you. Please.
If the delivery is internal to the node, how do the other nodes know the order of the delivery? Is that something that
They don't know.
They don't know, but that's the property.
The designer knows. What do you mean? You mean here, the nodes, the PJ delivers M1 before M2. Other nodes don't know that.
Yeah, but on the next slide, you say node does it in the order, delivers everything in exact same order.
Yes.
But how do
I know that? Because it's a property of the algorithm. But the nodes don't know that. It's a very good point. This property is a God's eye property, yeah? This property, you might deduce it from the algorithm, but the nodes cannot observe that. They don't know that.
But they have to somehow agree on the order.
Well, they're running a certain piece of code, And one of the properties of that code is this. But they don't really know that. They don't know that the other nodes are running that code, but you, the designer, you know it. So there's a difference between what the nodes know and what the designer knows about the whole system. It's actually, if you want the nodes to know, you have to run an algorithm. In fact, that's something we can see. If you run a reliable broadcast, each node will run into code, but each node does not know when the algorithm is finished. That's a global property. In order to know that, you have to run another algorithm called terminating reliable broadcast that somehow tells each node when all the other nodes are done. That's actually a very hard algorithm, much harder than reliable broadcast. Okay? So the knowledge, what's known in a node and what's known in the whole system is totally different things. Okay? Okay? But we'll go maybe more into that later on in the course. But that's the notion of what a node knows and what the whole system knows, what the developer knows, is totally different things. Okay? The nodes have only very limited knowledge, actually. But let me go back to these nice little exercises. Okay? So this example here, is this a single source FIFO? Is it satisfying single source FIFO? Yes or no? And then is it totally ordered? And then causally. Is this single source FIFO? This is single source FIFO. Remember what I told you about if conditions, okay? And the caveat here. Is this a single source FIFO? Yes? 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 Why? It's not because I am doubting, I pretend to doubt that I'm really doubting, no?
Because basically the message is sent from A or B array to everyone in the same order. But
what does this mean? If one node broadcasts two messages, is there one node here broadcasting two messages? No. So what does that mean? What's this property?
well, it cannot fail.
It's true, vacuously. Okay? So yes, it's true, but because nothing is making it false. What about total order? Is this an example of total order?
No.
No, why not?
Because it receives before one message than the other and vice versa.
Yeah, so here you have A, B, and here you have B, A. So this is not total order, that's clear. Is it causally ordered? Here's a nice question.
Yes,
Yes, why?
because again, there are multiple messages being sent.
They are concurrent. There's no causal connection between A and B, so the order doesn't matter. Okay, so they are causally ordered, huh? Okay, more funny examples. Here's a nice one. So here A and B are now being broadcast from the same node, but they're delivered like this. Is this single source FIFO? Here we do have two broadcasts on the same node, huh? So you might think, yeah, so this is like more in the case of single source FIFO, huh? So is it single source FIFO? It has to be, what is single source FIFO? First in, first out. So A before B, but what order are they delivered here? Is it FIFO?
No.
First in, first out? No, so it's not single source FIFO. Okay. Is it total order? Am I satisfying total order here?
No.
Yes,
Oh, here both a yes and a no?
because both of them both nodes got their messages in the same order.
Same order, so BA, BA. So it is total order. It doesn't have to be the same order, huh? Is it causally ordered now? So A is causally before B, yeah? That's clear, huh? A precedes B. So is this causally ordered? No, huh? But it's pretty clear, huh? Because B is delivered before A, huh? Okay. One more fun little exercise. So here I have A broadcasting, and then after it's delivered on the second node, I do a B broadcast. So is this single source FIFO? Single source FIFO? Put the emphasis on single. You know the condition for single source FIFO, huh? You need two. So what's going on here?
No, this
No,
two messages.
No node is sending two messages, so it is single source. Nothing is making it false. Okay. Is it totally ordered? A, B?
No.
B, A, it's not totally ordered, huh? What about causal? Well, I mean, A, B, B, A. So? No, huh? Not causally ordered. Okay. Interesting, huh? Little exercises to get your sense of specification. Okay. Now, let me show another interesting thing. We have seen a bunch of causal, of broadcast algorithms. Huh? So here I am showing 9 broadcast algorithms. Okay? So the arrow is stronger versus weaker. Okay? Ordering. And the weakest is best effort, which is not satisfying very much. The strongest one is uniform reliable causal. I haven't actually shown it, but if you replace the reliable broadcast by uniform here, you will get a uniform reliable causal. And the FIFO is very similar to causal, except it's weaker. You don't have to manage all causality, just the FIFO property, which is a subset of causality. Yeah? So you could take a look at the causal algorithms. I mean, a causal algorithm will be FIFO, but you can make you can make them weaker by only managing, for example, by keeping track of, by counting messages going from one node to another. So for each pair of nodes, you can implement FIFO algorithm. So it's a good exercise, actually. The code is quite simple to write these FIFO versions. So that gives us 9 broadcast algorithms. Interesting, huh? So we have seen already 9. So broadcast is not so simple as you might think. So what does your application need? Well, take your pick, right? Okay, but total order is not there. Where does total order fit in this diagram? How would I add total order to this diagram? Where does it fit? Is it down here? Here? Is it there? Where is it? Where does total order fit? Interesting question, huh? So total order, yeah?
The bottom right corner, since it's so strong.
Where would it fit? How would it compare to reliable causal, for example?
It would be stronger than reliable causal.
Is it stronger than reliable causal? No. Really? You sure about that? That means an algorithm that has total order broadcast is causal. Is that true? That would mean it's stronger. Really? Really? You sure about that? Let me
same order, so the causal relations are.
Let me show you something here.
So this is total order. Everyone delivers in the same order. It does not have to be the send order. Okay, but for a causal, does it have to be send for causal? In terms of if the for a causal algorithm, if A broadcasts before B, does it have to deliver before B for causal? Yes, because A is causally preceding B. Causal preserves the order,
We should get it after.
but total order does not have to satisfy that. Only the delivery has to be the same order. So total and causal are not comparable. You can't really compare them. There's not one that's stronger than the other. Total does not imply causal, and causal does not imply total. Total, we don't care about the send order. Whereas in causal, we do care about the send order. Okay? So where does total fit here? It's
Uniform
not
reliable.
sorry,
Bottom left.
bottom left.
Because like
Where would it be? So it's stronger than
it's,
but-
but weaker than FIFO because like it doesn't have to be FIFO as we've seen for having total there.
sorry. Say it again.
We don't have to have FIFO for a total there. Like one
No,
thing
we
doesn't
don't have
equal
to
the
have
other
FIFO.
one. So it's weaker than FIFO, but at the same time everyone has
It's
to receive
weaker
all
than
the message.
FIFO.
It should be weaker.
Is it really comparable? I mean, FIFO does not imply total order, and total order does not imply FIFO. In fact, maybe I will put you out of your misery. You can actually add total to any one of these. So it's orthogonal to all of them, in fact. So it doubles the number of algorithms. You can make a best effort total. So best effort, it's basically the sender. If the sender survives, then it's good. So we can make that total, huh? If the sender survives, everybody is receiving in the same order, fine. But if the sender dies, it's not. So total is actually orthogonal to this. That means we have seen 18 broadcast algorithms. Nice, huh? So you see, the simple idea of broadcast is actually not so simple. Of course, they're not all useful, huh? They're not all really useful. Reliable causal is useful. Uniform sometimes. FIFO, it's actually only when we're interested in point-to-point communications, okay? Even best effort is sometimes useful because it's so simple. But maybe all 18 of them are not as useful. Total order is actually complicated because it requires consensus, which we have not seen yet. It's more complicated than this. So you have to do a lot of work. Achieving total is a lot of work. So maybe you don't really need it, okay? Okay, great. Let's end there for today, okay? So that's all I'm going to talk about. So I think that gives you lots of good information, huh?